dark matter neutrino interaction from 21 centimeter cosmology.
So first, I will introduce the dark matter neutrino interaction model, and then I will move to its effects on CMB, and then finally I will move to my work, the dark matter neutrino interaction model on reionization history, and then finally I show the results. So, as we know that the vanilla lambda-CDM model of cosmology has so far been well established in the light of cosmological observations. Apart from some tensions like Hubble tension, some cusp core problems, and here the dark matter is assumed to be non-relativistic and non-interacting with other species. However, from particle physics models of dark matter, it often requires that the dark matter to interact with the standard model particles. For example, the dark matter baryon interaction in phase-out mechanism. And another interesting possibility is that the dark matter neutrino interaction. So this mainly useful for the thermal production of MEV scale of dark matter, and it is difficult to probe such interactions with the terrestrial experiments. But the cosmological perturbations may have the imprint on such interactions, and possibility to constrain such, we can constrain such interactions from the CMB power spectra and the matter power spectra. So these are the standard cosmological perturbations equations for the non-interacting species. These are the equations for density contrast and the velocity divergence. And the observable CMB power spectrum is defined like this. Here, these are the term of the temperature fluctuation at large scattering surface and energy loss, and the Doppler effect and the Sachs-Wolf effect. And the observable matter power spectra is basically the square of the density fluctuation. And these are the modified perturbation equation for the dark matter neutrino interaction model, where we can see that the interaction basically drags the velocity divergences term for the neutrino and the dark matter. And here, this mu dot is basically the dark matter neutrino interaction rate, and is basically ensures the conservation of energy and momentum for this particular interaction. And the interaction parameter is defined like this, where sigma dm mu is a cross section for the particular dark matter neutrino interaction, and sigma th is the Thomson scattering cross section. And here for this particular model, we are only taking this particular interaction parameter as a model parameter. So these are the possible effects of this interaction in the CMB TT power spectra and the matter power spectra. And this is been basically done with the modified version of the class. And here we can see that because of this interaction, if we increase the value of u, the interaction, it will basically increase the Doppler peaks, and the shifts to the Doppler peaks shifts to the larger values of L. And since the neutrino, since this type of interaction basically delays the structure formation of the universe, we can see that there is a suppression in the power of dark matter at larger values of k, and also there is some oscillatory effect for this particular interaction. So these are basically the features. So we can see the suppression of power at small scale for k greater than equal to 0.2. And for the standard lambda CDM case, this is the equation for the dark matter density contrast. And for the interacting dark matter neutrino case, these are the expression for the delta dm, and this exponential part is basically responsible for the suppression of the power at large scale, and this sinusoidal part is basically leads to the oscillatory behavior. And this is the posterior distribution of the lambda CDM plus U and other one parameter, the annihilation parameter, using the Planck 2018 data. And this is has been done in our group, and we have taken the this from Paul et et al. Paper. This is U, and this is gamma. And so from this Planck 2018 analysis, we have surely see that the values of U, this basically the Planck 2018 data has put a constraint on the parameter U, which is of the order of 10 to the power minus 4. So please keep that in mind. And next, I will move to my work, that is the interaction of this model in the reionization history. For this, I think there is no shift in H0 and sigma 8. And the first question I did. Okay. In the lambda CDM parameter, I think. Okay. That I have to check. I don't know. So this is the second part. That is the dark matter neutron interaction on the reionization history. So I have done the semi-numerical simulation, and which is basically there is a three part. So first is the in-body simulation, and then the halo finder algorithm, and final is the reionization simulation. So initially, we are planning to do this in a higher grid size, 2144 cube grid size, but because of some computational problem, we are showing the results for very small grid size, 256 cube grid size, and the volume of the simulation is almost 18 megaparsec cube. And for the halo finder algorithm, the friends of friends algorithm is used, and here the M mean is of the order of 10 to the power 9 solar mass. M mean is the minimum mass for which can minimum mass of the halo which can host the star formation. And the final part of the simulation is the reionization simulation, which we are used the Reon Yuga code. And here the anion, the number of ionizing photons per dark matter halo is we are using the value 23.21 uh, uh, for our case. And this is the basically the linear matter power spectra at jet 124. We are basically put this linear dark matter power spectra as the input to the simulation, and we can see that if we increase the value of U, so there is a more suppression in the dark matter power. And in this analysis, we have used the two constraints. One is the ionization criteria, and the second is the anion constraints. So these are the plots for the QH1 and QH2 and XH1 for the mean and 2 sigma limits on these two parameters from the Planck data. The shaded region are basically the allowed region from the Planck data. And for our analysis, we have used the 50% ionization criteria at redshift z equal to 8. And the second is that we have used some values of anions, that is the number of free electrons which are escaping in the intergalactic medium per unit halo mass. So for population 2 stars, so this anion is basically a function of many parameters, where the F star and F escape. These are the two parameters which are pretty unconstrained parameter, uncertain parameter. And for population 2 stars, we have put that an upper limit on anion, which is of the order of 500. And our work plan is that to generate linear dark matter power spectra for different interaction strength U, and put linear matter power spectra as input to the n-body code, and then run the n-body, f of f, and rearn Yuga code, and to vary the anion from 23 to 500 in order to achieve XH1 0.5 at redshift 8. So this is the final result of our simulation, where we can see that if we increase the value of U in order to satisfy the two conditions, the 50% ionization condition, and we have to increase the values of anion, and basically increasing U, it basically delays the ionization. And we can see that if we from these two constraints, the 50% ionization condition and if the upper limit of anion, we have put some upper limit on the dark matter neutrino interaction parameter, which is of the order of 10 to the power minus 7. And this is the main findings of our result, that is from reionization physics, we get much more stringent constraint on the parameter U. But in the previous case, which I have told that from the similar, from this particular model, if we use from the Planck 2018 data, the constraint on U is of the order of 10 to the power minus 4. So these are the output from the simulation, the nonlinear matter power spectra and the brightness temperature power spectra. And we can see that the nonlinear matter power spectra decreases as we increase the value of U. And similarly, if we see the brightness temperature power spectra, this is for the lambda CDM, and if we increase the value of U, so the brightness temperature will increase, and this basically helps to detect the signal. And these are the H1 map for the particular models, for the particular values of U, which we have chosen for our case. And these all maps are generated for XH1 equal to 0.5. And we can see that as we know that if we increase the value of anion, there should be more number of ionizing photons which will enter the intergalactic medium, and it will eventually increase. For this, the ionized bubble should also increase. But here we are seeing that more or less the pretty similar type of nature for these ionized bubbles. So this is maybe the case for because we have used very smaller grid size for our simulation, and the resolution is not pretty good. That's why we are not getting this particular information. And the second is next is that we have estimated the noise power spectra from the SK1 low observation, and these are the particular form to estimate the noise power spectra. And we can see that if we increase the observation time, the noise is basically decreases. And we have compared our result with this particular noise power spectra, and we have seen that the signal is much higher than the noise power spectra for K1 to 2.5, 0.5 to 2.5. And this basically tells us that there is a possibility to detect the signal from SK1 low observation. So to summarize my talk, so what we have basically done is that the 21 centimeter observation improves the constraint on dark matter neutrino interaction by few orders of magnitude, and the high SNR will imply a possibility to detect the signal. And now we are trying to do this particular simulation in a using a better simulation specification. And also we are doing the forecast analysis on the cosmological parameters in the reionization and post reionization era. And another point is to make that there is another paper in the archive which shows that uh, they have also used the similar kind of technique, and they also did the simulations, but they used the gadget kind of simulation. And they also show that the constraint, the upper limit on the dark matter neutron interaction U, which is of the order of 10 to the power minus 8. But what we have found is that the U is the upper limit on U is of the order of 10 to the power minus 7. So we do not know what is the cause of this tighter constant. Maybe because we have used some a very we have used the simulation in a very short grid size. So that may be the reason. So thank you.
Thank you. So
I just have two suggestions. Okay, one is that you said that one of your goal would be to use at z equal to 7 to reach hi equal to 0.5, right? I think the paper that you are referring to is Mitra Chaudhuri Ferreira in 2016, the PCA analysis. But 2016, the data that was available was Planck 2015. After that, a lot of part of, as I was discussing, part of early reionization scenarios has been ruled out by Planck new data. So present bound would be around 7. You go to XHI equal to 0.5 or something like that. Just check this one because this might have changed. Okay, if they have updated that with a newer version of their paper. And the second is that the matter power spectrum has a suppression with certain kinks as well. Probably SDSS, if not SDSS, DAISY, Dark Energy Spectroscopic Instrument, will have already have the data around certain region, 1 megaparsec inverse or something like that. So probably there are already data that you can make use of. I'm not sure if they are public, but maybe class or Kobaya has the likelihood already callable from their routine. So please.
So I was just wondering about that. Like anion, your simulation also have other free parameters like minimum halo mass, which can host ionizing source. So instead of changing anion, if you change, yeah. So I mean, how that fit into your study?
So we have not checked that particular point, but we will definitely check.
Okay. And also the mean free path of.
Right. Our mean free path.
Thank you.
So following up on Dheeraj's question, does this effect of U is also there at redshift 2.5 on dark matter power spectrum?
Redshift 2.5.
2.5.
Yeah, I think there is a effect of the dark matter power spectra at that redshift.
Yes, because SDSS EBOS data is already available, power spectrum from Lyman alpha forest. DAISY will be available, and then there is another survey called VIV QSO, which will be available in next 5 or 6 years or so. So you might want to consider comparing with the Lyman alpha forest, which is already observed. I mean, the data is very well constrained, the power spectrum basically. Yeah. Thanks.
Hi. So I was wondering, since your simulation volume is this small, what kind of mean free path did you use? I understand you did not change the minimum halo mass. So
I have used, I think, 20 megaparsec.
okay, and what was your simulation volume?
18 megaparsec cube.
Okay, so did that not like cause any? Because I am also running Real Yuga. So did that not cause any sort of discrepancies if your mean free path is like larger than your simulation volume?
I think from the other data, the arming free path should be of 20 to 60 megaparsec.
I see. Okay. Thank you.
Okay, any other question or comments? Okay, if not, let's thank Antara and also thank all the speakers for this session today.